All right, so now that we've had some practice counting atoms, it's time for us to use that skill for something really important to chemists, which is balancing chemical reactions. So let's find out what balancing is all about. Well, first of all, it's based on the law of conservation of mass, which states that during a chemical reaction, mass is neither created or destroyed, simply redistributed among the products. So we don't add mass, we don't remove mass, it just keeps getting jumbled among the different chemicals. Balancing means ensuring that every reactant atom can be found in a product and vice versa. So you can't create an atom, you can't destroy an atom, just like we can't create or destroy mass. A balance reaction has coefficients. Those are those numbers that we had in front of symbols when we were working on counting atoms. And that number shows us how many of each of those materials we need for balancing. Lastly, those coefficients multiply every number of atom inside that entire compound, but stops whenever you get to a plus sign or a reaction arrow. It doesn't carry on any further than that. So let's do a quick review of types of reactions. A skeleton equation, SE, skeleton equation. We had this one for the combustion of gasoline, which was C8H18 plus O2 makes CO2 and water. But you'll see that there's 8 carbon in that gasoline, but only 1 carbon in the carbon dioxide. Similarly, 18 hydrogen, but only 2 in the water. So we know that there's a whole lot of atoms that are just disappearing here. When this gets properly balanced, we'll have coefficients, like 2 and 25 and 16 and 18. Now, those are pretty big coefficients. Usually they're not nearly that large. So we're about to go through the process of how we get those numbers. So on we go. If you need to pause the movie at this point, that's the last point on this slide. Okay, going on to the next slide. The tool we're going to use is something called an ELR chart. Now, ELR stands for element, left, and right. And it's simply a chart to record the number of each type of atom we have in a reaction. So here's our first reaction. So we've got CaCl2 plus Li makes LiCl and Ca. Now I didn't mention it before, but you can't change the symbols. CaCl2 is calcium chloride, Li is lithium, LiCl is lithium chloride, and Ca is calcium, and we can't change any of that. So on the right hand side here, I'm going to draw a 3-column chart. And I'm going to label the columns E for element, L for left, and R for right. So when I look at the left-hand side, I see that there is 1 atom of calcium. So I'm going to write calcium. And I see there's 1 atom of calcium. I also see that there's chlorine. And I see that there are 2 atoms of chlorine because of the subscript 2. Still on the left-hand side of that reaction arrow, I have lithium. And there's no subscript, so it's a 1. Now I'm going to go to the right-hand side. Right-hand side means right-hand side of that arrow. I have 1 lithium. Notice that the order has changed. I have 1 chlorine. And I've got 1 calcium. Now, balancing means that I've got the same number of every element on the left and right. And so when we compare the calcium, we see it's 1 and 1. That's good. When we see the lithium is 1 and 1, that's good. But the chlorine is 2 and 1, so that's not good. So what I normally do is I underline the smaller side. I underline the lower side because that's going to tell me where I need to add a coefficient. And I'm going to add a coefficient somewhere on the right side that'll get me more chlorine, because chlorine is what I need more of on the right. So I find my lithium chloride, because that's where my chlorine is, and I have to ask myself, how do I get 2 chlorine? And the way I get 2 chlorine is I write a 2 as a coefficient. And as soon as I do that, I get 2 things happening, because that 2 distributes over the lithium and the chlorine. So that means I'm going to have not 1 lithium, but 2, and not 1 chlorine, but 2. And so at this point in time, we're saying, great, I got the chlorine balancing at 2 and 2, but I messed up my lithium. Don't worry, that happens all the time. It's very, very common. you're going to see it so many times that you suddenly get used to it. Calcium is still fine. Chlorine is now good. Lithium is now 1 and 2. And remember that underline the side which smaller, because that's where we're going to add. Lithium on the left-hand side is just the element lithium. It's all by itself. These are really nice because then I can put a 2 there, and 2 times the 1 lithium is 2. And so now I've got 1 calcium on the left and right, 2 chlorine on the left and right, 2 lithium on the left and right. This is what we call balanced, and as soon as I've got it all balanced, I go back and fill in all my extra blanks with a 1 to show that the coefficient for each of those happens to be a 1. And so this is fully balanced. All right, so let's try another one. Example 2. So this is that sodium bicarbonate that we used in our skills unit, and I'm just going to draw a solid line underneath here to stop that one and move on to the next one. And so we can see that there are sodium, hydrogen, carbon, and oxygen. So we got 4 different elements here. Left-hand side, there's only 1 chemical before that arrow. So I can just quickly look, and there's 1 sodium, 1 hydrogen, and 1 carbon because there's no subscript. With no subscript, that just means there's 1 of each. Oxygen has a subscript, so I can see how many there are. There's 3. On the right-hand side, it's a little more work because we've got 3 different chemicals. Now, the sodium has a subscript on the right-hand side. It's a 2, so there's 2 sodium. Hydrogen on the right-hand side in the water has a subscript of 2. Carbon on the right-hand side has a no subscript, so that's 1. Oxygen, however, is in all 3 of them. And so oxygen, when it's in several compounds, you have to add them up, just like the plus sign show. So in Na2O, there's 1 oxygen. In H2O, there's 1 more oxygen. And there's 2 oxygen shown by the subscript in the CO2. So 1 plus 1 plus 2 equals 4. So I'm looking at my ELK chart now, or ELR chart. I got 1 sodium, I'm short sodium, I'm short hydrogen, and I'm short oxygen. So I got a lot of work to do here. So I'm not quite sure where to start, so I'm just going to pick something. I'm going to start on the left-hand side is where I'm short, so I'm going to put a 2 here. And I'm going to hope that that gets me really, really close. So the sodium, well, all these numbers double. So it's going to be 2, 2, 2, and 6. All of those double. And so now the sodium is good, the hydrogen is good. The carbon, which was good, is now bad. And the oxygen wasn't good before, and it's still not good. That's okay. We've seen this before. You're going to mess them up before you get them better. Now the right side, carbon and oxygen are the small ones. Well, let's deal with carbon because oxygen's in several different compounds. So carbon on the right has 1. We needed to use up both of them. So if I put a coefficient of 2 in front of the CO2, that means 2 carbon and 2 times 2, which is 4 oxygen. So the carbon's now 2. That's great. There's 4 oxygen here, plus 1 oxygen from the water, so 4 plus the 1 is 5, plus another oxygen in the Na2O for a total of 6. So this is now balanced with 2 sodium on each side, 2 hydrogen on each side, 2 carbon on each side, and 6 oxygen. Last step here, go back, fill in the 1s. All right, so if you need to pause at this point in time, this is a good spot. Okay, last slide. Okay, so 2 more examples. Example 3. We're going to draw one of those ELR charts. And so we have E, L, and R. This time that's that tarnish reaction from your writing reactions. So we've got silver, sulfur, and aluminum. Left-hand side, we see the subscript 2 for the silver. There's no subscript on sulfur, so there's 1. No subscript on aluminum, so there's 1. On the right-hand side, the silver, there's just 1. The sulfur, there's a subscript of 3. In the aluminum, there's a subscript of 2. So we're going to need, on the right-hand side, more silver. On the left-hand side, we're going to need more sulfur. And on the left-hand side, more aluminum. So a good rule of thumb is anytime you need to do multiple things, go to the thing that has more atoms attached. Leave things like aluminum metal and silver metal for later. So I'm going to look at the Ag2S and the Al2S3 and say, okay, well, I got to fix those. So I'm going to try first with the Ag2S. And since I need 3 sulfur on the right, I have to put a 3 on the left in front of the Ag2S. 3 times 2 is going to give me 6 for the silver. And 3 times the 1 understood is going to give me 3 sulfur. So my sulfur is now good. Silver is not good, but it wasn't good before. I also need to increase the amount of aluminum on my left. There's 1 by itself. I'm going to need 2, so I can just put a 2 in front of the aluminum. And now the aluminum's good. Aluminum's now good. Sulfur's now good. Silver just needs to increase from 1 to 6. So coefficient of 6 in front of the silver brings the right-hand side up to 6. Everything's now balanced. Fill in the 1 on the Al2S3. If you ever find yourself not filling in a 1, you need to check to make sure that you can't divide everything. We need simplest ratios. So if you ever get a situation where you don't have 1s, check to make sure you can simplify, see if you can simplify the ratio. Last one. Ooh, now we got brackets. Now, some people think brackets are a huge problem, and I don't find the brackets a problem at all. So we're going to draw that line. A little squeeze for space here, but I'm going to put the Al, and I'm going to put, well, all the nitrogen and all the oxygen always stays together in that nitrate group. So some people, what they'll do is they'll go NO3. They'll talk about those NO3 groups as groups, Fe and Br. Sometimes that NO3 package works, sometimes it doesn't. You have to look to see if all the nitrogen and oxygen always stay together as a package, because sometimes they do and sometimes they don't, and it only works if it stays together. So we should be getting kind of comfortable with this. The aluminum on the left is 1. The subscript outside the bracket on the nitrate is a 3. So there's a 3 there. Iron is 1 because there's no subscript, and the bromine is 2. Right-hand side, we see the iron is 1. The nitrate outside the bracket has a subscript of 2, so there's 2 nitrate groups. The aluminum, there's 1, and the bromine, there's 3. All right. Now, something that we'll see a lot of times is this. If we look at the bromine and see a 2 to 3 ratio, if I put a 2 in front of whatever gave us 2 bromine, that's going to give us 4. So we're going to end up with 6 bromine. So if we know we're going to end up with 6 bromine, because 2 times 3 is 6, put the coefficients to get us there. That means a 3 in front of the FeBr2 and a 2 in front of the AlBr3. And let's see where that puts us. So the bromine, of course, on the left goes to 6, iron goes to 3. On the right side, the bromine goes to 6, the aluminum goes to 2. All right, so we're short aluminum, we're short iron on the right, aluminum was on the left, and we've still got that 3 to 2 ratio, but I'm really not wanting to work on the nitrate things right now. I'd hope something else will fix that for me. So left side, I need 1 more aluminum, so I'm going to put a 2 in front of the AlNO3 bracket 3. That gives me 2 aluminum, but it gives me 6. 3 times 2, which is 6, the nitrates. Again, looking at the iron, I need a 3 in front of the Fe bracket NO3 close bracket 2. So that brings me up to 3 nitrates, or sorry, 3 iron, but 3 times 2, which is 6 nitrates, and so my nitrates work out beautifully. Hope this helps. You've got a worksheet to work on. Enjoy.